everybody. My name is Ergi Pramana. Today I'm honored to present an essential topic in geometry, which is geometrical transformation. So let's begin with the types of transformation, right? There are four fundamental ways we can alter the position or size of a geometric figure. First is translation, which can be thought of as slide. Second, we have reflection, which is simplify a flip. Third is rotation, which means to turn around a central point. And the last one is dilatation, which is a change in size, right? Next. All right, to understand the mathematical language behind transformation, we must look at the notation. The original figure before any change occurs is called the pre-image. Then the figure we get after the transformation take place is called the image. When mapping points, we use a prime notation to distinguish them. For example, the original points A, B, C will transform and become A prime, B prime, and C prime. So, next. All right. Now let's discuss about congruence transformation. In geometry, congruence means identical, and transformation means change. There are three congruence transformation, which is translation, reflection, and rotation. These are unique because even though the figure moves or flips, the original shape and the transform image remained completely identical in size and shape, right? Next, let's look closer at the first type, reflection. A helpful reminder, reflection are flips. It involves folding or flipping an object over a straight boundary called the line of reflection. An object and its reflection will always have the exact same shape and size, but the figure will face in opposite direction. And most importantly, every point on the image and its corresponding point on the image are at an equal distance from the line. When mapping reflection on a coordinate grid, we apply specific algebraic rules depending on the line of reflection. The first is reflect over the x-axis. The reflection of the point x comma y in parentheses across the x-axis is the point x comma minus y in parentheses. Next, we have the reflect over the y-axis. The reflection of the point x comma y in parentheses across the y-axis is the point minus x comma y in parentheses. The third one is reflect over the line y equals x. The reflection of the point x comma y in parentheses across the line y equals x is the point y comma x in parentheses. For a reflection across the line y equals negative x, the point x comma y in parentheses become minus y comma minus x in parentheses. All right, moving on the other types of reflection. Fourth is reflect over any line. Notice that each point of the original figure and its image maintain the same distance from the line of reflection. On a grid, you can easily determine this by simplify counting the distance from the line. And the last one is reflect in the origin, which is 0, comma 0 in parentheses. In a point reflection in the origin, the image of the point x comma y in parentheses is the point minus x comma minus y in parentheses. Next, our second major transformation is rotation. Always remember Rotation are turns, while the orientation change, the image retains the same shape and size. This rotation can go clockwise or counterclockwise. When solving these on coordinate plate, we follow standard mathematical assumption unless told otherwise. First, we assume the center of rotation to be the origin point, which is 0, comma 0 in parentheses. And second, we thread a positive angle as counterclockwise and a negative angle as a clockwise, right? Uh, Next, let's define the standard counterclockwise rule for rotating points around the origin using the unit circle, right? For a rotation of 90 degrees, x comma y becomes minus y comma x, right? And rotation of 180 degree when x comma y becomes minus x comma minus y, and rotation of 270 degree x comma y becomes y comma minus x. Let's remember uh, clockwise and counterclockwise. Right? Let's put this into a practice with an example of a 90-degree rotation. We start with a triangle ABC with the coordinates a uh, we're going to A 1 comma 1 in parentheses, coordinates B 1 comma 5 in parentheses, and the last one coordinate C 4 comma 5 in parentheses. By following our 90-degree rule, where upon when x comma y in parentheses maps 2 minus y comma x in parentheses, our new image coordinates become a primes minus 1 comma 1 in parentheses, b prime becomes minus 5 comma 1, and the c prime becomes minus 5 comma 4. All right, next. The third transformation is translation. A quick reminder, translation are slight. Historically, the word translate originates from Latin, meaning carried across. We describe a translation by their factor movements, such as sliding an object 5 units to the right and 2 units down. The resulting image will always look exactly like the pre-image, keeping the same shape, size, and pointing in the same direction. Next is translation rules. Here are the core rules for translation. First, a translation is isometric, meaning it preserves length and it also preserves orientation. Second, we represent translation t of point A to A prime by TA, right? A x comma y in parentheses maps to A prime x plus A, comma, y plus b in parentheses is written as t a equals t of x comma y in parentheses, which equals x plus a comma y plus b in parentheses, right? And the last one is it can also be written using a column factor notation where point A, comma B is represented vertically. Uh, T of column factor x, comma y equals column factor x prime, comma y prime, which equals column factor x, comma y plus column factor AB, resulting in column factor x plus A, comma y plus B. Next, we have example. Let's analyze this graphical example where a triangle is shifted 6 units left and 3 units up. The general transaction mapping is up is x comma y in parentheses maps to x minus 6 comma y minus plus 3 in parentheses. If we apply this to the original point a where 2 comma negative 2, we calculated 2 minus 6 to get negative 4 and negative 2 plus 3 to get 1. Therefore, A prime successfully mapped add open parenthesis minus 4 comma 1 close parenthesis. Next is dilatation. Our final type of transformation is dilatation. Unlike the previous three, dilatation changes the physical size of the object. The image will retain the exact same shape as the original, but it will scale to a different size. When a dilatation creates an image that is larger than the original, we call it an enlargement. When it creates an image that smaller than the original, we call it reduction. All right. Next. Let's review an example of dilatation on coordinate graph. Dilatation always require a scale factor, which we label as k. In this particular case, our scale factor k equals 2, right? The coordinate of our original pre-image are a negative 2 comma negative 2, B 1 comma negative 1, and C 0 comma 2. To delete the figure, every coordinate is multiplied by the scale factor of 2, giving us our final image coordinate is A prime at minus 4 comma minus 4, B 2 comma minus 2, and C 0 comma 4. Right? That's bring me to the end of my presentation. So thank you very much for your time and your wonderful attention. If you have any question, I would be happy to answer them now. So thank you.